So today we're going to be going over chemical kinetics. Kinetics is going to be the study of reaction rates. An example of a slow reaction rate would be like rust growing on a pipe, which can take months to a year, or an instantaneous reaction like an explosion, which happens immediately. So today we're going to be using the lambda max, or the maximum absorption, to track concentration changes. We're going to be looking at colored systems, which essentially is the absorption of light through conjugation. So typically conjugated systems are going to be an alternation of single and double bonds. If that conjugation, or the order in which the single bonds and double bonds are orientated, is disrupted, we'd no longer absorb light in that specific spectra. Today we're going to be using the microlab as a spectrophotometer to monitor the changes in crystal violet over time. We're going to be tracking the crystal violet still in solution, and so to do this we need to come up with a rate constant, or a rate law. So for the rate law, what we're going to be incorporating is, of course, the equilibrium or rate constant, the concentration of hydroxide in solution, as well as the concentration of crystal violet in solution. The hydroxide will be raised to the reactant order X, and the crystal violet concentration will be raised to the exponent Y, which is just the individual reactant orders. So for the safety procedure, or the protective wear that we're having to wear today, we want to make sure that we have goggles with a protective side, just to make sure in case anything splashes up, it doesn't get directly into our eyes. Of course, we're going to be using gloves, as well as pants which go completely to the ankles. We don't want to be exposing any skin. For long hair, we want to make sure that we tie that back just in case it doesn't fall into any of the chemicals, as well as closed-toed shoes. We don't want to be exposing any extra skin, and of course, make sure that we have our lab coats on.
Okay, so now that we heard about the theory for the experiment, now we can get started with the actual fun part. For today's experiment, we're gonna need various things. We're gonna need graduated cylinders, we're gonna need beakers, we're gonna need pipettes, pasture pipettes, and we're gonna need vials, all of them with the same size, where we're gonna put our solutions that are gonna go inside the spectrophotometer. Now, one of them will be filled with DI water, and this is gonna serve as our blank for the calibration of the experiment. So I'm just gonna fill it up with water, and I'm gonna put it on the side until we're ready to calibrate our instrument. So now I'm gonna prepare my solution, where I'm gonna put the crystal violet into the beaker. And I'm gonna follow that with the sodium hydroxide, and I need to make sure that I do this as quickly as possible, because the moment I add the sodium hydroxide, my reaction is beginning. So I'm gonna pour that in there, give it a quick little swirl, and then pour it into the vial that is gonna go straight into the spectrophotometer for absorbance measurements. Now, do pay attention to the color, because at the end of the reaction, we expect it to be clear. So now that I already have my first solution prepared, I'm gonna switch gears to working with the second solution. And this time I'm gonna use 0.05 molar sodium hydroxide. And it's very important for us to look at the labels, because even though it's the same chemical, we're using different concentrations, and we don't want anything to be mixed up or cross-contaminate. So our next step will be to place the vial with the water inside the spectrophotometer. Okay, so now that we have our blank read by the spectrophotometer, I'm gonna take the vial out. This is my DI water, and now I'm gonna get the crystal violet solution with the sodium hydroxide. I'm gonna quickly put it in the spectrophotometer to allow it to measure the absorbance over time. Now I'm gonna click start on the computer and allow it to measure the absorbance over time. Now that the 15 minutes are up, we're gonna press stop on the computer. Now we're gonna tie things back to the theory that was discussed previously, and we're gonna click on the bar graph, specifically at 590 nanometers on the graph that corresponds to the lambda max for crystal violet. Once we have that graph pulled up, there's different tabs on the computer that we can look for the order of the reaction. Now the reaction's either going to be 0, first, or second order with respect to the crystal violet. Once I find the order of the reaction, I'm gonna click on Curve Fit, which is a tab on the computer, and generate a linear line. So now that I have my linear line, the computer is gonna generate a curve fit. And it's very important to note the curve fit because the slope of the line is gonna be the value for K on the lab report. So now with what we've done thus far, we're gonna repeat the same process, but with the next concentration of sodium hydroxide, so we can generate 2 linear curves for each solution. So now that we have the graphs with the linear curves, we need to save and print so we can focus on the math.
So going over the calculations for experiment 14, we need to set up a rate expression. So the rate expression is going to be equal to K, the rate constant, multiplied by the concentration of the reactants. So we're going to be having sodium hydroxide or hydroxide, as well as the concentration of crystal violet. You'll notice that each one of these is raised to an exponent, which is going to be the reactant order for that specific reactant. Now, the first reactant order we're going to solve for is going to be crystal violet. So we're looking at the exponent for Y. So to do this, we're going to add an excess of sodium hydroxide in solution. Therefore, we can kind of manipulate this out of the equation. So normally crystal violet and hydroxide is in a 1-to-1, but now we're going to add a mass excess of the sodium hydroxide. So what we end up with, and what you'll see on equation 2, is rate multiplied by K prime, which we'll explain later on, is equal to the concentration of crystal violet raised to the Y. You'll see that to solve for Y, we're going to have to plot the information from your microlab in a couple different ways. The other thing to really notice or pay attention to is that the concentration of your products is equal to absorbance. Those are going to be a directly proportional relationship. So if you're able to get a very linear fit or an R squared close to 1, for the concentration versus time, this is going to be indicative of a 0th order reaction. There's going to be a 0th order dependence for the concentration of crystal violet in solution. For a first order reaction, we're going to have the ln of concentration versus time. And for a second order reaction, this is going to be the inverse, or 1 over concentration versus time. The other thing to notice here is the way that slope is going to be generated. So is it going to be just slope is equal to K, which you see for a second order reaction, or for the 0th and first, we're seeing slope is equal to negative K. So once we've established a reactant order for crystal violet, we need to do the same for the sodium hydroxide or hydroxide concentration. So as mentioned before, it's really important to generate these lines from the microlab from the spectrophotometric data. So for the original 0.05 sodium hydroxide in solution, this is going to solve for K prime. So the line generated for that experimental section is going to be equal to K prime. Now, K double prime is coming from when we double that concentration, so you'll have 0.1 molar sodium hydroxide in solution. So depending on how those reactants, the concentration of those reactants change and the overall change in the rate for that reaction is going to dictate that order. So mathematically how we do that is we need to do a ratio. So that'll be K double prime over K prime is equal to 2x. X, of course, being the reactant order for sodium hydroxide or hydroxide. Now, algebraically, we'll just do log of base 2 of that ratio, K double prime over K prime is equal to x. So by this point, we've already solved for the reactant order for crystal violet as well as the reactant order for sodium hydroxide. Now, we can do some approximations to get the actual K, as well as solve for the molar absorptivity coefficient, which you'll see in the last section of your lab report. So this is the basic setup for the calculation section for experiment 14. If there's any further questions, go ahead and make sure to contact your TA.